Okay, so now we're going to talk about choose as functions. Before, the last questions that we were just asking is how many ways can I choose k objects from a group, from a collection of n objects in order. Now we're going to ask without caring about the order. So let's say there's a raffle and every person in the raffle wins a free cruise. You don't care if you were picked first, second, or third. You might not even know if you're picked first, second, or third. You just care if you were picked. So if we have A, B, C, D, Alice, Bob, Charlie, Dave, and Emily are picked, we can pick at random from the set 3 people who are going to win the raffle. So then we can do Alice, Bob, Charlie. We can do Alice, Bob, Dave. We can do Alice, Bob, and Emily. We can do Alice, Charlie, Dave. We can do Alice, Charlie, Emily. We can do Alice, Dave. We can do B, C, D, B, C, E. And then B, D, E, then C, D, E. And this should be all of them. So I'm just going across in order. And then once I run out of new objects for my second element, move on to the next second element. Cool. So if I correctly listed all of these guys, then we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hopefully 10 options. So this guy, but this is actually very similar to our other question. So our other question was how many different ways are there to pick them in order? So, and that gave us 5 factorial divided by 3 factorial. Sorry, 2 factorial. Because it's n factorial divided by n minus k factorial. K is 3, n is 5. So this is very similar. So, but it's actually less restrictive. So any different ordering. So if I had A, B, C, and A, C, B, or B, A, C, or A, B, C, A, C, D, B, A, C, B, C, A, C, B, A, or C, A, B, all of these 6 options would all be the same collection of objects because I don't care about the order. So how many objects are there in this? Well, this is k factorial because k is 3, so we've got 3 objects. So in this case, what we actually have is n factorial divided by n minus k factorial divided by k factorial. So what would we get if we plug that in? Well, we would get 5 factorial divided by 2 factorial times 3 factorial. So what is that? That is 5 times 4 times 3 times 2 divided by 2 times 3 times 2. So that cancels there. And we are left with 10, which means that it worked in this case. And that essentially that explanation that I'm going to give you, or that I just gave you, can be changed into a general proof of there are n factorial divided by n minus k factorial ordered sets that can have their order disregarded. This is not a formal proof, but this is just the general sketch of how you would turn this into a formal proof, and it'll be a good exercise for you to do to try and fill in all of the details and make this more formal. Ordered sets that can have their order disregarded by dividing by k factorial, because there are k factorial collections, or ordered collections with the same objects. So this is just the sketch of what would be the proof. And this guy comes up all the time. It's going to come up particularly when we talk about probability. But so just give you guys one more example. 1 second. Okay, so actually, first thing to note, this is how we normally write this. So this is how we'll normally write n choose k, and mind that's n factorial minus k factorial times k factorial. So this is also the same thing as n choose n minus k, right? Because we would get n minus k is just equal to k, and then so that's there, and then we would have the n minus k factorial there. So just by kind of reordering it, we can see that this guy is the same thing as this guy, which makes sense if we just think about, so this is basically an algebraic proof for it, but if we just think about the meaning of these things, this is saying how many different ways are there for me to pick n minus k things to put, or how many different ways are there for me to pick k things to put in this box. But that means that I'm leaving n minus k things in here. I can just ask how many different ways are there for me to pick n minus k things to leave in this box. So we're essentially asking questions that look identical. So that would be what's called a proof by appealing to the combinatorial meaning. This isn't a fully sketched out proof, but that's the essence of what it would be. You say that, hey, these two things that I'm counting would result in the exact same thing. And now if we, another thing to note is that the sum of n choose k from k equals 0 to n is equal to 2 to the n. Right? So how do we know this? Well, what is n choose k is just asking how many subsets of order k are there. Given a set with n elements. So if we add up all of the sets of size 0 plus all of the subsets of size 1 plus all the subsets of size 2 all the way up to all the subsets of size n, then that's just asking how many subsets are there of a set with n elements, which we already know that's the cardinality of the power set. So to prove this statement, we can add up. We can get the power set. Cardinality power set. That's what that cardinality of the power set by adding cardinalities of sets of order k for k in 0 to n, which is just the meaning. So that right there provides a proof. And it'll be good for you guys just to run through some computations. So to write out or compute 4 choose 1, 3 choose 2, 3 choose 1, 4 choose 2, 3 and 5 choose 3. So compute those guys. And